Hi, I'm Isaac from the Boston Data Science Meetup group. Yeah, and tonight we obviously have Layne Sadler talking. A couple of quick things. Yeah, the Boston Data Science group sponsored by Mass Mutual, so we thank them for helping to sponsor the event. Great to do a kind of co-hosting with PyData Boston. Actually, for a while ran a PyData chapter up in Orono, Maine, so always get to host with PyData groups. So anyway, so getting to our speaker, so Layne Sadler definitely has an interesting talk coming up tonight on AI quality control framework. So Layne is has a background and is currently working on this open source framework to manage some of the problems with deep learning and kind of reproducibility, which is a very big area, and kind of the quality of machine learning models. I think anyone who's in particular worked with deep learning has run into a lot of problems managing hyperparameters, tuning models, and making sure the models run correctly in a production context. So it's always good to see a talk that addresses it. So yeah, with that said, I'll hand it over to Layne, and hopefully we learn a lot about his AIQC framework and how it can help with those problems.
All right, thank you so much for the intro, guys, and thank you for hosting the meeting. I'm going to go ahead and grab the old screen share. So just a quick little agenda. First things first, we'll talk through some slides about the origins and challenges that I was looking to solve in building this framework. Then we'll take a quick look at the documentation so you can figure out how to install it, look at what the difference between the high-level API and the low-level API is. GitHub repos right here. Any stars, much appreciated. And then finally, if time allows, we'll go through a demo of the high-level API on either some image data or some Kepler satellite data for tabular. So here's a high-level look at the framework. What it does is it helps you rapidly prepare data in the form of splitting and folding, and then rapidly encoding. Just by setting simple variable names. And then after that, it breaks the single model paradigm by allowing you to hypertune models in batches. And then finally, it automatically calculates performance metrics and charts for all of that. And the goal in doing so was really just to take a lot of the tedious manual code out of the process of deep learning, both the preparation of the data and training of models, just because I was working on a paper and I was trying to show comparative metrics, and I was using some remote server, and I was like, this is just getting absolutely out of hand. So how could someone that's really new to the space go in and do a good job? And at the same time, I've been working in genomics as a product manager in the analytics space with Big Pharma on national biobank projects to look for drivers of rare disease. And I was just kind of blown away that they weren't using machine learning. They weren't using deep learning. It wasn't even discussed. They were still using statistics and pretty early forms of it. So I was wondering, what are some of the challenges that are holding researchers back from adopting deep learning? And when you think about it, it's really pretty simple. Most of the researchers I've been working with have been PhDs, and they're biologists and doctors. They're not programmers. Scientist doesn't necessarily mean data scientist, and it definitely doesn't mean software engineer, right? So I think the emergence of informatics in each space, we're going to start to see that change, and it'll work its way more into education. But for now, most of the people I was working with, they really were yearning for a user interface where they could just click a few buttons and run their models, right? And the other side of that is not only were they not programmers, but they weren't machine learning experts. And this is, again, not to slam any people. These are some of the smartest people in the world. And also, if I bring up a competitive technology, I'm trying to toe the line with code of conduct, and I'm just bringing it up for like a survey of methods out there. Finally, when you do dig into machine learning and deep learning, it really is pretty loosely defined. If your script lines up nicely, you won't get errors deep in your training runs. But it's pretty easy to run into that kind of scenario if you don't really know what you're doing. And when you contrast that to like quality control processes in science, you can see how they would view machine learning as a black box. And then finally, not everyone has the money to work with a data robot or use cloud-based methods. A lot of people are still using, on-premise HPCs. So this creates a real challenge that prevents the adoption of deep learning at a time when we have a lot of problems to solve here on Earth. So I was thinking to myself, could I come up with some bumper rails around this process to make it easier so that it can be adopted at a higher rate? And I was coming at this from a Django perspective, where everything was like MVC, so I had a lot of experience there. And at the same time, we were using Jupyter at work, and I was learning data science, so it all just kind of naturally came together into a nice framework. I had also been working on my own paper, so I had access to some academic guidance. I was looking at neural networks as graph data structures with edges and nodes, just like any other graph. And I was trying to make more informed predictions based on that information. So I got access to, I sought the highest council of my order, and they said, you're doing great, but you can't really have a paper if you're not using validation splits or crossfolds, and I need to see comparative evidence of every run that you've done if you actually want to publish this paper. So I kind of viewed that as a quest, right, to go out and learn some of the best practices of deep learning. And I found these 3 chronic problems riddled in, hard-coded into pretty much every solution out there. And we're going to step through some of these in action, but there are a lot of sources of bias, and they don't necessarily have to do with how training is done. It's more about how the data is prepared, and that's why I chose to focus on that. Initially, I was looking at, can I just come up with a way to, functionize my model and pass in hyperparameters nicely, because everything else seems kind of complex, but I was naturally drawn towards these problems in data. So, the first is that fundamentally, we've been evaluating on our test split. So, let's say you run your model and it is doing some learning, like you're above 50%, and you see you've got 74% accuracy on your test, pretty decent learning on your training data, and you make some changes and you see, okay, yeah, they're both going up, but it looks like I've got a pretty good model, but it's not doing perfect on the test. So again, you make more changes, and the problem with this is that you're biasing, you're overfitting, you're effectively using your entire data set to train your model, which really defeats the purpose of splitting up the data in the first place. So I'd call this evaluation bias, and it's kind of unavoidable because we are humans and we're looking at this kind of process, and we're making our own model in the back end that says these params are giving me this, and this is coming from the latest book on fast AI. They've got a lot of great theory out there. So that's kind of the first one. And if you want to solve this, the problem is that validation splits are really, they're second-class citizens. They're not widely used. This is the classic 70-30 split, using the train test split that everyone's familiar with. And if you want to do this and introduce a validation split, then you have to kind of run it twice, basically. And this introduces math, which is lame in the Python world, at least. And then if you take this further downstream and you look at how data is actually being encoded, let's say you are using something like cross-fold validation, where you're rotating which fold you're using to evaluate your model, and then finally you're running it on the test split. A lot of what I saw was that people were just encoding the entire data set. So all this aggregate information from both test and validation is being leaked into, it's actually transforming the training data. So your averages, your power transforms, your scaling, it's all biasing the training data. So that's the leakage problem, right? And these are they're chronic problems. They're everywhere. And this is just like, if you wanted to actually do it properly, you would encode each split or fold independently, so that you're not sharing information across them. And then finally, I mentioned the oral history of machine learning, right? So when you get started, pretty much every data type is handled differently. Like we were talking about images and natural learning and time series, it's all practically a different science. And then each data type is follows its own different protocol. And this is kind of what I'm talking about. If you look at scikit-learn and the encoders, I love scikit-learn, right? I use this in AIQC, but the columns represent different data types. And then on the left-hand side are the different encoders that you can use, at least the ones that are in capitalized letters. And then a 1 represents if it works, and a 0 represents if it doesn't work. So there's a lot of trial and error in figuring this out. Additionally, like some of these allow you to modify data in place, some of them don't, so you have to handle the data differently. So these present challenges to newcomers. I remember the first time I was like, what, I have to encode my data? I can't just, throw it into some magic model. These are problems that people face. And then finally, what I was originally going to solve was training and scoring models by hand. And what I found was that there are some good solutions out there. But if I thought about this and I said, I don't want evaluation bias, I don't want data leakage, so am I going to have to manually feed in crossfolds individually? And what does the setup look like for this? I'll show that in the next slide, because these solutions that I was running into, they really felt like they were intended for programmers, not people that were trying to do science. And then finally, they focus more so on the data just kind of shows up, right? And then you're only focusing on the parameters in the model itself. So here's kind of the different starting points. This was step 1 in the process, and it was setting up YAML files, and it just seemed like a lot of programming, like parent run and child run. I still don't really know what that is. I'm assuming there's some kind of branching going on, but not great for a biologist. And here, just to show some praise, I think Weights and Biases did a great job in just having a really simple callback for recording your weights. There's a lot of different things you can do with callbacks. And then RayTune, you pass it in a config, it's got some nice hyperparameter optimization, and you give it your training function. But again, where's the data, right? And the problem that I have with this is it's mainly nomenclature, right? I'm so sick of seeing X and Y. I always forget what they are. Just call them features and call them labels. And that right there was kind of the basis for AIQC in treating things as objects, like a feature, a label, a data set, a split set, an encoder set, just because it's all just scripting. And if you only look, if you show up with the data, you have no history of the data. Like if you told your high school science teacher that, I don't know, I used like 70% of the samples, that shouldn't fly. And that shouldn't fly for the FDA, right? If you want to actually take data science seriously, you need to have a good reproducible workflow when it comes to data lineage. So I made this framework. On the bottom right, you can see it's just a downloadable Python package. You pip install AIQC. It acts like an MVC framework in that there's objects for everything that you would expect, like a feature and a label and a data set, like I mentioned. And those all get recorded in a local SQLite database that you don't even have to set up. It just, when you import the package, it automatically it creates a file and creates tables within there, and you can just start working with the objects. And we'll take a look at the high-level API, but in literally it's effectively 2 lines of code, even though there's a lot of variables. You can ingest your data sets, split and fold them and encode them, run a model in batches with hyperparameters, and we'll see how it spits out all the metrics. Then, maybe someday I'll make an enterprise product out of it too, but for now I'm just having fun, adding support for new data types. So from here, are there any questions? I don't have the chat up, but I there aren't that many of us. So I would like to field questions if people do have them.
I don't see any put into the chat at this point in time, but if anyone has any, go ahead and put them in the chat, or we can take them at the end as well.
Okay, great. So the framework itself right now, it supports tabular data and image data. Doesn't yet support text and graph data. I think time series is just going to be 3D tabular. And then right now it supports classification, both binary and multi-class, and then also regression or quantification. And it supports Keras right now. In the future, it'll be really easy to add support for PyTorch just because I'm pickling models. So they're just kind of serialized strings and functions, basically. But this is the documentation portal, AIQC.read the docs. You do a pip install AIQC, import AIQC, and then this one-liner right here is going to create a, it uses aptors. So this is what application support looks like. This is where you're supposed to be installing applications, not just at like the very root. But you can see if I navigate into the AIQC folder, there's a SQLite file. And, oh, I'm not sharing that screen. But anyways.
Hey, Layne, we've got a few questions popping up. Do you want to tackle?
Sure. Yeah. That'll break up the flow a little bit.
Okay, we got a couple from Adam, one of the co-organizers from the Boston Data Science Group. Are there any libraries you tried to use that weren't quite what you were looking for when you decided to build your own library?
Any libraries that you tried to use that weren't quite what you were looking for? Yeah, so I fundamentally am not a big fan of SQL Alchemy, so I was looking for an alternative to that. And I wanted to use Django, but the interface with Jupyter is not really that fluid. So I ended up using, I'll just type it into the chat. It's kind of embarrassing, and the author thinks it's embarrassing, but the library is called Peewee, and it's an ORM. And it stresses simplicity. So it makes it really easy to interact with a SQLite file, which is just a SQL database as just a file. So there's no ports, there's no shenanigans, there's no binary install or anything like that. It's really easy and really nice to work with. So I highly recommend it. Let's see. Can you explain the difference between Keras and PyTorch? So Keras is just a high-level API for TensorFlow. When you try to interact with a TensorFlow API, it's kind of Greek, and it's hard to do in native Python, I feel, at least. So Keras just really boils that down into a sequential model. That PyTorch, they're starting to become one and the same, and you can pretty much kind of use them the same. They're going to have the same type of layers, the same type of hyperparameters, so that is more so. But a lot of people gravitate towards PyTorch because it's highly custom, and you can get really in depth with like the functional API, whereas Keras is designed more so as a high-level API. So that's why the legit people use PyTorch, but I don't know, I've had pretty good luck with Keras. And when you talk to people a lot in the field that are doing this kind of work, a lot of them are still even just using TensorFlow. So there's that. Am I looking for developers to contribute to the project? Absolutely. Yes, I forgot to say that at the start. I actually can't join PyData as a solo contributor. So I welcome people wholeheartedly. If you're interested in natural language processing, not an area I have much expertise at. If you're interested in working with time series data or generative models, yes, absolutely welcome. And yeah, just feel free to send me an email, and I'll put that in the chat right now. When you say Keras, that means there's no specific use of TensorFlow. Not right now, no, but they handle model pretty much to add a support for a new library. I just have to handle the model output objects, and I just got Keras done because that's what I use, and I kind of moved on. But yeah, definitely need to add support for that. Can this be incorporated into standard QA and BD testing frameworks? It's just a Python library, literally. So I don't see why it couldn't. And then the fact that it's just a SQLite database and you don't need some kind of weird connection means that if you have a file system, you can work with it. Yeah. The examples look more like scikit-learn pipelines. Is there anything? Yeah, so anything fundamentally different other than using Keras. So I think that is kind of a good point to jump into, the demo, right? So if I pull up, so this is a running Jupyter instance, right? And if I come in here into this, let's start here just because it'll be simple and it's built in. So I've got some example data sets built into the package, and I'm gonna go ahead and import it and make sure it's all working. It's a decent amount of code, and I'm gonna import some libraries, it looks like. So within the data module, I've got a bunch of data sets already built in. So I'm just going to grab this one. It's kind of a classic binary classification example. So you can see it's pulling it up right here. And then maybe let's start with the high level API, because that's a good place to start. But when you feed data into something like scikit-learn, you're really just giving it like a NumPy array, right? And when you give it a label, you're dividing it into like X and Y. And I introduced a few wrappers around that, like label and feature set. That's probably the simplest example. But there's an object for pretty much every kind of action that you want to take. So it's a guided experience. So all of the commands you would need to run can be boiled down into one call to pipeline. And then when you're making a model in experiment, when you have an algorithm, you give it a bunch of hyperparameters and feed it into the experiment. Honestly, I looked at scikit-learn pipelines a few years ago, and like 3 months ago, and it just didn't feel intuitive to me. It just didn't feel, it felt like the library wasn't originally designed to do that, and it felt like it was kind of being forced to do that. So I said, can I take kind of a fresh approach on it, using its great encoders and using its great splitters and crossfolds. But then like when I do something like a split or a crossfold, I'm recording the indices of each and then persisting that. So I'll just, let's take a look at what that actually looks like here. So if you're to take this data frame, the sonar data set with all, the labels and the feature sets, what you do when you create a pipeline is you specify the type of data that you're making, and you pass it either the file path. It supports CSV, TSV, Parquet, and I really like Parquet because it preserves D types very well. But you can also give it a pandas data frame or an ND array. And what it wants you to do is tell it, which column is the label. And then the high level API just assumes all the remaining columns are features. It lets you specify the size of your validation split and your test. You don't have to split the data manually. It's just going to split it and record that as a split set. And then if you wanted to do crossfold validation, you would just say 5 here. And if you wanted to do stratified binning, you would just say 3 stratified bins there. So it is like an abstraction layer for scikit-learn when it comes to the data processing. I love it. I think it's very powerful. And then if you want to encode the label, you pass in a scikit-learn encoder, like an actual scikit-learn encoder that I've just imported up here. And if you try to do something wrong, like if you try to use a numerical encoder on a categorical, it won't let you. It'll actually error to help users out. And then you can pass in an entire dictionary of feature encoders. So here you can see you can either rule columns in or out. So, and you can chain them together. And so if you have to split up your data, it will actually join them back together. So you can run many different encoders based on the type of data that are in your features. So here I'm using a power transformer, and I'm saying only target the float data type. Yeah, so let's go ahead and run it, and it'll tell you, it'll actually go and so that you don't get an error when you're training, it'll test the encoding of each column, and if you're out of columns, it won't let you add more encoders, right? So these are the kind of validation rules that I've been introducing on top of it. Here, let's see. So the next thing you want to do is build an algorithm. So a bit like PyTorch Lightning. I actually didn't know PyTorch Lightning existed, but you divide the model up into the build phase, the train phase, and then you give it hyperparameters, and then you pack it into an algorithm object, and then you feed that into an experiment. It allows you to parameterize it. I haven't added transfer learning support to this yet, so you could ultimately skip the model build and model train and do like a fast AI type approach where you're just using pre-trained models. So if we define this model here, and then we define what training looks like, you know, the batch size, the number of hyperparameters to run, we might get an error because I haven't actually checked these hyperparameters and made sure they still line up with the model. But again, it's just pickling these objects, and then it's going to access them later, and it's going to pass these hyperparameters in as keyword arguments. So you can do really nifty things. Like here, I was trying to test an activation of leaky ReLU versus ReLU just using an if statement. And in this convolutional example over here, you can see you can get really creative and say, like, I want to use this many blocks and just treat that as a hyperparameter. Like here, I've got conv blocks to use. So it makes it really expressive, and you can treat the entire topology pretty much as a parameter. But let's see if we can go ahead and actually run this. So previously, before Python 3.8, I was running this as a background process, but now it just runs in a foreground process. But I mean, that's kind of how everything else works anyways. So while that trains in the background, let's take a look at some of the metrics. So this is running all the jobs based on the hyperparameters that I specified. And the metrics get automatically calculated for every single split. So if I'm using a train, validation, test, split, it's going to calculate metrics for each of those independently. And you can say hide test if you wanted to get really strict about evaluation bias. Here is an example of some of the plots that are automatically produced behind the scenes for every single run. You have something that helps you compare entirely different runs. So because I was generating so many different runs, I needed a way to compare across models, right? So this is an entire model, the train, the validation, the test, and then this is a different model, the train, the validation, the test. I call this the boomerang chart. Haven't really seen it elsewhere. You can, again, everything's persistent, right? So you can just say, show me the hyperparameters that were used, getting this ID, getting this run by ID. The learning curves are all recorded, so you can see what's going on. These charts are all interactive. And if I'm running a regression, I'm going to get different plots automatically generated based on the type of analysis that I'm conducting. So here, and there's even different metrics too, right? So classification and regression are handled kind of entirely differently. But let's take a look at, I'm going to interrupt this run right here. And just to show you, like, boom, for the jobs that we've run, these are all the metrics. And I can set a threshold for performance and loss, again, based on the type of analysis that's conducted, different metrics are used. And I can just visualize. So yeah, this totally bonked on the test. It looks like, you know, maybe it's not. It lends itself to interpretation of models pretty nicely. So again, I'll stop there. The repo is github.com/AIQC if you're interested in getting in touch and collaborating. So thank you so much for the time. Awesome.
Thank you so much, Layne. And we do have one more question so far that's been put in, also from Adam again. You mentioned before that you are accepting collaborating with other developers. Do you have any low-hanging fruit issues or easy things for someone to work on who might want to contribute?
You know, the first thing that comes to mind is feature importance, or even adding support for PyTorch, again, because it's just kind of like pickling objects, handling the binary file, and writing it into SQLite. So that's definitely more than welcome. And another one that comes to mind is imputation, right? So if there's missing values, I'd like to have like an imputer set, similar to the way that there's an encoder set, so people could just kind of drop something in there. Yeah. Thank you for asking.
Awesome. Yeah. Any other questions? This is our question and answer time. So if there are any questions, either put them in the chat or you can unmute yourself and just ask them verbally. So just take a minute, see if there's any more questions that come up for anyone. It was a great talk, Layne. Thank you so much.
Thank you again for having me.
It's like a really.
I've got a question, if that's all right.
Go ahead.
Well, thanks. Hi, I'm a tester, so I'm always interested in from that perspective, from the QA perspective. I'm just wondering if you've had any. I mean, I assume it's easily done because it is just a Python library. But have you had any examples, or anyone you've heard of use the tool to integrate it into, say, an MLOps pipeline or a DevOps pipeline sort of thing?
Integrating it? No. I mean, I literally just finished writing it a few weeks ago, and just said, hey, let me come up for water and see what's going on, and think about how to position it. And you know, I would say this is almost for an organization that's pre-ML ops, and this could kind of serve as an ML ops solution where they're thinking about getting into deep learning. Maybe their analysis is kind of static, and they don't necessarily need to have like a very fluid real-time pipeline that's pulling data on a schedule into models, but it could sit in there, and you could use any, again, it's just a Python package with different modules, so you could use different aspects of it in your pipeline. Like if you didn't want to use the data pipeline, maybe you could skip that part. Unclear on, but writing tests is another area where I could use help. I just kind of wrote like a tests.py and ran through all the examples, and I run them when I write new code. So, you know, something like PyTest could be very helpful. Unclear on how you overcome the evaluation bias issue. Can you expand on that? Yeah, sure. So in the low-level API, there's, I'm going to share screen. It always shows you like 1,000 windows, you know? So when you're creating in the low-level API, if you're creating a batch of jobs manually, you can say hide test. And what that is going to do is it's going to keep your holdout data out of the metrics and out of the charts. So you won't even know. You'll get performance metrics on your train, and you'll get performance metrics on your validation split. So there you're just taking a small slice, and then if you're getting good performance on both your train and your validation split, then it's more likely that your model is going to generalize well when you throw it at the unseen holdout split. And again, you don't have aggregate transformations like encoders that are being run on the entire data set. They're run on each split or fold separately. So you can kind of stay blind from the test, if that helps answer the question. And just to, you know, one last bit on that, like if you are running and you're eventually going to want to see the test data, right? But if you're doing like 30 runs on just train and validation, and only then, once you've got like good performing parameters, you start applying it to the test holdout set, then you haven't really designed your model. You're just kind of waiting for a hit on your model that catches and learns well. And you're not really architecting it around the test set. You're kind of getting lucky with a run. And there's even a repeat count. So you can run this same model like 10 times or 3 times just to give it a chance to actually learn well.
Great. Any other questions coming up for anyone? All right, looks like we're probably, oh, B. Wilson, are there any specific limitations of scale?
Yes, absolutely. So when I ran the Jupyter 2021 survey, I was really blown away that more people weren't using cloud clusters. The majority of the analysis being done was performed on local desktops or HPCs and servers. So people were just kind of stuck with what they've got. And this works in that scenario 100%, but like in the future, I'd like to have a cloud API where you could just kind of like offload, once you have your batch of jobs designed, you could just kind of blast them into the cloud. They all run in parallel, and the time it takes to run one model, you could pull it down. But for now, yeah, it just queues up the jobs, and you run them after getting the cut. You take the trash out, and you've got your models. But yeah, it's going to be limited to the resources that you have on your computer.